I'm back with part 2 of that particular my project. So as you remember, my name is Gandhi Kansil and my project is based on evolutionary algorithms and developing new techniques for it. We have covered the analysis of genetic algorithms and now we will move over to the new approach which I have developed. So guys, I have told you about crossover and mutation. Now my technique is basically it has it deals with a new kind of crossover and mutation operator. I have defined it as a XOR operator because that is what it does. Now in case of crossover, the older algorithms I've explained to you, the new algorithm is that when we take the two parents, now the bits of the first parent are taken if a randomly generated number is less than or equal to a predefined number, uniform rate. And if the random number is greater than the uniform rate, then we take a XOR of the parent 1 and parent 2 bit and then put it into the child's chromosome bit. And for the mutation step, it's very simple. We just run the generated child's chromosome through a loop which goes from position 0 to the last bit of that particular chromosome, of that particular child's chromosome. So for every bit we generate a random number, and if that random number is greater than the predefined mutation rate, then the child retains its original bit. That means that if that number is greater than the mutation rate, then the child remains as it is. If the number is less than the mutation rate, then that child's bit is XORed with a rounded off random number between 0 and 1. That means that we take a random number, we round it off, and then we take a XOR of it with the original child's bit, and then we put the new bit into that child's for that particular bit segment. Now I have developed a program for it so that I may be able to better demonstrate to you how it works. Now this is a genetic algorithm program which works on an old algorithm. Now here in case of crossover, as you can see that if the random number is less than uniform rate, we set solution from parent 1, otherwise we set the solution from parent 2. Now this is a usual crossover program. Now in the new algorithm, how it works is that we just loop through that individual size, that is normal. If the random number is less than the uniform rate, then we set the bits of parent 1, that is also the same. Now the change is when the random number is greater than the uniform rate, then we take a XOR of individual 1 genes, that means the parent 1 genes with parent 2 genes. This is the XOR of them. We convert it into byte and then put it into the child. So guys, this is the crossover part. For the mutation part, here it is given. Now the normal mutation method is also very simple. We just loop through the child and then we check with a random number the mutation rate. If it is less than the mutation rate, then we put in a randomly generated number which is rounded off so that it becomes 0 or 1 into that particular child's gene. In my algorithm, the change is that we loop through the child, that is the same. If the mutation rate is less than the random number, then we take a byte, that is 0 or 1, through the previous method. Then we XOR that with the particular gene, that particular bit of the solution, and then we put in that XOR into the child. So in this way it differs. Now let's run it. The old generation is giving now. I hope you are able to understand why it's giving different solutions every time, because of these random numbers. Now these random numbers, because of them, as you know, the population is also set through the random function. So this random function, because of it, we sometimes get individuals which are closer to the original function and sometimes which are far away from the solution. So we have to run it a multitude of times so that we get an average. Now for this particular algorithm, that this new one, this old one, sorry, the average number of generations which I have found out are 21. For the new algorithm, the average number is first 16, then 22, 17. Don't worry about it. The average number was somewhere around 15 and 16, so it performs better, and hence we get a solution which is performing better than the things which we have tried to find. So with this, I'm going to take your leave. I hope I was able to clarify what genetic algorithm means, and I was able to convey how my algorithm works. Thank you for watching. This is Gandhi Pencil signing out.